Hello, everybody. I'm going to talk about some motion problems using definite integrals, just so that we can get kind of a clearer grasp on how this is going, and then we can be successful moving forward. So let's just start off with position. So position, let's say, is s of t. Now, we've talked about the way that I get from position to velocity, so to v of t, is by taking the derivative of my position function with respect to time. All right? And we call this ds dt. So I'm actually going to write that real quick. So this would be ds dt or dx dt, which we know is the rate of change of position, which is equal to our velocity. And then I can get from this, if I take the derivative of velocity with respect to time, it's dv dt. We know that that is equal to acceleration, because acceleration is the rate of change of velocity. All right? Now, we can do the reverse of this. So if I start at the other end of this with a of t, and let's say I want to get from a of t to v of t, well, I do this by taking the antiderivative, or by undoing the derivative of acceleration. So a of t dt equals v of t. And then I can do the same thing with v of t. If I want to undo v of t, well, I take the antiderivative of v of t, which then equals, I'm actually going to make this a little bit smaller. Maybe not. So then this all over here, boom, this is not going well. This mess at the end here is the antiderivative of v of t dt, which is equal to x of t. All right? So let's look at an example. So let's say that I've got a of t is equal to 1 meter per second squared. All right? And I also tell you that v of 3 is equal to negative 3 meters per second, and s of 2 is going to be equal to negative 10 meters. All right. And what I want to know is, what is v of t? What is v of t? All right. So what I need to do is I need to go from a of t to v of t. And I do that by taking the antiderivative. So v of t is equal to the antiderivative of a of t dt, which is equal to the antiderivative of 1 dt. Now the antiderivative of 1 dt is going to be equal to t plus c. I need that c there because that represents my unknown constant. All right, that could be 0, but we need to verify what it is before we move on. I can verify what that c is by plugging in what was given to me, this condition here. V of 3 is equal to negative 3. So I've now got v of 3 is equal to negative 3. So let's go ahead and plug that in. I can say that negative 3 is equal to 3 plus c, which means that c is going to be equal to negative 6. So I end up getting that v of t is equal to t minus 6. All from the information that was given to me there. All right? Now, we can do the same thing with our position as a function of time. So if we come over here, I've now got v of t is equal to t minus 6. And our condition here was that s of 2 is equal to negative 10. So I need to go from velocity to position. So again, we're going to be taking an antiderivative of this. So I can say that s of t is equal to the antiderivative of v of t dt, which is equal to the antiderivative of t minus 6 dt. Now the antiderivative of t minus 6. So this is going to be I'm going to add 1 to the exponent here, so that's going to be t squared, and then I'm going to divide by that new exponent, t squared over 2. This will become minus 6t, and then I need that plus c to account for that unknown. Now I'm going to plug in my condition here. So s of 2 is equal to 2 squared divided by 2 minus 6 times 2 plus c. And this right here is equal to negative 10. So I get 2 squared divided by 2 is 2. 2 minus 12 plus c is equal to negative 10. So 2 minus 12 is negative 14. So I get that c is going to be equal to 4. So I get that my position as a function of time is equal to t squared divided by 2 minus 6t plus 4. Now we can check this to make sure that these functions match up. So now I've got s of t is equal to 1/2 t squared minus 6t plus 4. I've got v of t is equal to t minus 6. And I've got a of t is equal to 1. So if I want to get from s of t to v of t, then I need to take the derivative of s of t. So v of t is equal to ds dt. So dt of 1/2 t squared minus 6t plus 4. So just a whole bunch of power rule here. So I start here. I subtract 1 from, so I bring down the exponent. So I get 2 times 1/2 t. And then I take t to the 2 minus 1, which is 1, minus 1, because I bring down that exponent, times 6 to the t minus 1. So that's going to be t to the 0, plus 4. Now that 4 is going to go away, so it's going to be plus 0. So I get that v of t is equal to t minus 6, which checks out with what we started with. Now I can get a of t by taking the derivative of v of t. So a of t is equal to dv dt, which is equal to d dt of t minus 6. And when we work this out, we end up getting that a is equal to 1, which again matches with what we had expected. All right, guys, so that's a real quick version of what the goal of taking the derivatives and integrals of our position functions are. Obviously, these were relatively simple functions, but the premise remains the same. All right, hopefully this was helpful, and I'll keep giving you guys more examples. Talk to you guys later.